An air conditioner that runs but doesn't cool is one of the most misleading service calls in the trades because the system sounds fine. The blower's running, the condenser's spinning, everything looks like it's working, but the temperature won't drop. This video is going to change how you approach that call. By the end of this walkthrough, you'll have a repeatable diagnostic sequence you can use on any split system, residential or light commercial, and you'll know why most techs waste time by starting in the wrong place. Step 1. Airflow first. Here's why. A restricted airflow condition mimics low refrigerant almost perfectly. Suction pressure drops, the coil gets too cold, ice starts forming, and if you misread that as an undercharge and add refrigerant, you've now overcharged a system that had a dirty filter. Check the return filter. Check the evaporator coil face for dirt or ice buildup. Check that every supply and return register in the building is open and unobstructed. A system needs adequate static pressure to move the right volume of air across that coil. Without it, the heat exchange process breaks down, and your gauges will tell you a story that isn't true. If airflow checks out clean, move to Step 2. Step 2, refrigerant charge. You're looking at two pressures, suction and discharge, and you're cross-referencing them against the outdoor ambient temperature and the indoor wet bulb temperature. Do not, and I mean this, do not just look at a pressure chart and decide the system is low. Pressures are meaningless without temperatures. For a TXV system, you want to check superheat and subcooling. For a fixed orifice system, you're checking superheat at the suction line. Low superheat with low subcooling usually points to an undercharge. High superheat with high subcooling often points to a metering device issue or restriction. These are different problems. They require different solutions. Take the measurements, do the math, let the numbers tell you what's wrong, not your gut. Step 3, the metering device. A TXV that's stuck closed will starve the evaporator. You'll see very low suction pressure and high superheat. It looks exactly like a low charge, but adding refrigerant won't fix it. You'll keep adding until you've overcharged the high side, and the system still won't cool. A TXV that's stuck open does the opposite. It floods the evaporator, superheat drops to almost nothing, and liquid refrigerant can slug back to the compressor. The diagnostic tell, change the load on the system, and watch how the suction pressure responds. A healthy TXV modulates, a stuck valve doesn't. If the valve isn't responding, that's your problem. Step 5, the compressor. A weak or failing compressor is one of the most expensive diagnoses you'll make, which is exactly why you want to confirm it with data before you say the word compressor to a customer. Start with amp draw. Pull your clamp meter and compare the running amperage against the nameplate RLA, rated load amps. A compressor pulling significantly below RLA while pressures are off is telling you it's not compressing efficiently. Then do a valve test. With the system running, check your high side and low side pressures. Shut the compressor down. Watch how quickly the pressures equalize. A healthy compressor holds differential for longer. A compressor with blown valves equalizes almost immediately. If your pressures collapse fast and amp draw is low, you have compressor valve failure. Document everything before you write the estimate. Step 5, electrical and controls. The last category is electrical, and it's the one that causes the most head scratching because the failures here are intermittent. A weak capacitor is the most common electrical cause of a cooling problem. The capacitor helps the compressor and condenser fan motor start and run efficiently. When it degrades, the motor works harder, runs hotter, and sometimes trips on thermal overload. Test capacitance with a meter. Don't eyeball it. A capacitor can measure low while still looking physically fine. Also check your contactor for pitting or burning on the contacts. A contactor with high contact resistance creates a voltage drop that can cause a compressor to run inefficiently or short cycle on overload. And if the system has a communicating control board, check for fault codes before you do anything else. The board already knows what it detected. Use that information, so there's your sequence: airflow, refrigerant charge, metering device, compressor, electrical. If this breakdown helped you think differently about your next service call, there's a full refrigerant charging video that goes deeper on superheat and subcooling calculations. That one's worth watching before your next residential job.